All right, I'm going to try to make this fast. We did a ping pong ball lab, if you were not here. And so I'm just going to run down through. You were supposed to have watched the video that I had posted and then answer the questions, some of the questions first before you watch the rest of the video and then watch the rest of the video. So let's just do a quick recap here of what we had talked about. So what is a force? Again, that's something we had already talked about. It's in your notes, in your comp book, at least should be. Again, it is a push or a pull, but it's a little more than that. It's a push or a pull that happens between what? Two objects. Two. Not two or more, not one, but two. A push or a pull that happens between two objects. Now, what is a balanced force? Balanced force is when all of the forces on the object will not change the motion of the object. Those forces we would say are balanced. And back to this, what is a force between two objects? And this is why we name them the way we do. We name forces the way we name them because with agent object naming, because there are always just two objects involved. There's two things. One is creating the force. That's the agent. The other is receiving the force. That's the object. That's why we have agent object naming. That's why we always name them force of blank on blank. And those two blanks are the agent and then the object. Now, I've noticed that some of you are not putting names on the forces, which I've asked you to do. Again, the names on the forces are forcing us to think through, okay, who's the agent and who's the object? Who are the two things involved in this force? So anyway, and it says what happens when forces are not balanced? Well, when they're not balanced, then we do have a change in motion, which means there's an acceleration of some kind. All right, now with the fan and the ping pong ball situation, I was hoping you would realize that the force is being represented by the fan and the fact that the fan is moving air. Okay, and then what is representing the mass would be the actual ping pong balls, because one is only 2 grams, one's about 8 grams. They're very different in mass. One is 4 times more massive than the other. Now, what we ended up seeing in the video, which again, you were able to make predictions and then you were able to see the actual results because those were in the video. Now, what I don't know is if in the video you were able to see the actual results of this. I was assuming that everyone would know that the light ping pong ball with the fan on high would be the highest or fastest acceleration, and that the low fan with the heavy ball, that would be the slowest. So slowest, low fan, heavy ball. Highest acceleration, fastest acceleration would be the high fan and the light ball. Now, the middle two, that's the, I'm not sure. And so that's why in class we had to do some timing and figure that out. And almost every class figured out that the low fan with the light ball was actually faster than the high fan and the heavy ball. In other words, the higher fan speed was not able to overcome how much more massive the ball was. So that was a little slower. The low fan with the light ball was a little bit faster. And again, not a lot. We're talking a couple tenths of a second, not that much. Okay, so we found that out. Now down to these questions. So what happens to the light ping pong ball's acceleration when the fan speed goes from low to high? So light ping pong ball, low to high. What gets faster? What happens to the heavy ping pong ball's acceleration when the fan speed goes from low to high? It gets faster. So from your answers to numbers 1 and 2, what can you say about the acceleration when the force acting on the object increases, but the mass stays the same? If the force increases, but the mass stays the same, what do we know about acceleration? It gets faster, it goes up, right? And here, with the fan on low, how does the acceleration of the light ping pong ball compare to the acceleration of the heavy ping pong ball? So now, when the fan's on low, how do the accelerations of the two compare? Well, the lighter one had more, right? The heavier one had less with the same fan speed. Number 5, with the fan speed on high. So now we cranked it up to high. How does the light compare to the heavy with the fan on high? Again, the light one was faster because the less mass made for more acceleration when the force was the same on each of them. So, from your answers to questions 4 and 5, what can you say about acceleration when the mass of an object increases, but the force applied is constant? So the mass of the object goes up, force stays the same, the acceleration is going to decrease. I hope that's what you observed. That's what we just found out. Okay, that's what our predictions here. That's what our predictions are, or the actual results. That's what it told us. Okay, that the more mass of the object, the less it will accelerate. The harder the push, the more it will accelerate. That leads us to a conclusion that, see, this is what's called Newton's second law. Now, I don't know if you've created a force diagram for the ping pong ball, but if we had, this would be something of what it would look like. So we got a ping pong ball that's accelerating, right? Motion lines getting further apart. Ping pong ball is accelerating. And we have an unbalanced force diagram, okay? Unbalanced. Now, some people said this. Some people said that there was indeed another force here, and it was a force of friction on ping pong ball. Now, is that possible? Well, sure, but it has to be what? Hold on, let me put some. So that this one has to be balanced with that one. This one now clearly is not balanced with the other one. Okay, so the force of air is bigger than the force of friction on the ball, and so we have unbalanced forces, which is why we have acceleration. Okay. So even if you do think there is a friction force, which I mean, there is, and it's probably really tiny, which is why I drew the arrow so small. Now, what I did later in class is I took a ball bearing. I took a stainless steel ball bearing, which isn't a whole lot different in size than the ping pong ball itself. But this is 225 grams. This is 2 grams. This is over 100 times more massive. I mean, I'm talking this is heavy. And I put this down on the track between the meter sticks. And I turned the fan on low, and it would not move. The stainless steel ball bearing would not move, which tells us what? That tells us that the friction force here is probably as big, at least as big, as the force of air on the stainless steel ball. No longer the ping pong ball. Now we're talking about the stainless steel ball. Okay, that means the friction force is at least this as big as what the force of air was. Now, I turned the fan on high, and then the ball started to roll. So its motion changed. How does that change this diagram? How does that change this diagram? If I turned the fan on high now, and it started to roll, that would make the force of air bigger. Yes? Which means, because the friction force isn't going to change. I mean, the friction force on the ball bearing, it's big. Okay? Way bigger than it was for the ping pong ball. And then when I turned the fan on high, and it was able to change the motion of the ball bearing, then that means now that our force of air, I better get this over here a little bit, our force of air now is even bigger than it was because now the fan's on high. So that maybe, oh no, I need to redo this. Oh gosh. So that 2 marks, 3 marks on the other side. So now what I'm saying is, hey, this is unbalanced again. The ball bearing was able to actually roll with the fan on high, which means it changed its motion. It went from no motion to some motion. And not only that, it actually was getting faster, little bit by little bit, but it was getting faster, which means we had to have an imbalance here. Okay, we had unbalanced forces, which means the force of air was finally big enough with the fan on high, was finally big enough to overcome the force of friction on the ball bearing. So anyway, we took a look at that in class. And again, all of this is boiling down to something, and it's called Newton's second law. Okay. And what does Newton's second law say? It says that unbalanced force is equal to the product of mass times acceleration. You should be writing this down. So unbalanced force is equal to the product of, it is mass times acceleration. Okay. Which means that if you're unbalanced, it's also called net force. Another name for unbalanced force is called net force because it's the net result of all of the forces acting on an object. Okay, net force. And that equals mass, again, mass times acceleration. Now, if you think about this, and actually I can write it like this. If we look at A as F over M, which is how Newton said it. He said, hey, acceleration, whatever the force does, if the force gets bigger, then A is going to get bigger. If F gets smaller, then A is going to get smaller. That's what Newton said. And then he said, if you think about this, if the mass gets bigger, what does that do to A? If you think about this, if the mass increases, what does that do to the size of that fraction? If the mass increases, that means the fraction F over M, force over mass, that gets smaller. Mass increase would cause the A to do the opposite, which is inversely proportional the way we have it shown here. So what this means, and again, this is what Newton said, that acceleration is directly proportional to the force, but it's inversely proportional to the mass. The more massive an object gets, if the push remains the same, the more massive the object gets, the slower it's going to accelerate, which is what we saw with the ping pong balls, right? The more massive ping pong ball with the fan on the same speed is going to be slower accelerating than the lighter one. But both of the ping pong balls accelerated faster when the fan went from low to high. So when you increase the force, your acceleration is going to get faster. But when you increase the mass, it's going to do the opposite. So I hope that is clear. That's what Newton's second law says. Now, here's what we're doing with that. We are creating this thing called summation of forces, okay? We're going to sum the forces. Now, what I'm going to do is this. Oh no, that was not supposed to happen. I am going to select this right here. I'm going to move this force diagram, or maybe I'll just copy it. I'll copy it, and then I'll paste it down here. Maybe. Okay. Oh, perfect. So here's what we're going to do. We are going to look at the summation of all the forces that are acting on the ping pong ball. Okay? Summation of the forces. Now, this Greek letter here, this is a weird looking shape. That is a Greek letter called sigma, and it stands for summation. Okay? It is a symbol that means summation. So when you see a sigma next to a capital F, it actually means this phrase. like summation of forces. That phrase right there is what this sigma F means. It means we're going to add up all the forces. And then I'm going to go one step further and say this. We're going to add them up, all that are happening in the y. The y, that's up and down direction, vertical, okay? So if we look at our diagram, what forces do we have in that dimension? Well, we have a force of gravity, and we have a force of table. Now the question is, what do those add up to? What do those add up to? Well, did we decide whether those forces were balanced or unbalanced? They're balanced, right? We said vertically that gravity is doing exactly what the table is doing, equal amounts, right? But they're opposite direction, which means one of them has to be what? Negative. Typically, we would say that the downward direction would be negative and that the upward direction would be positive. And so if they're the equal amount, but one's positive and one's negative, when you add them up, what do you get? Nothing, right? We would say maybe that they cancel out, they cancel each other because we have a positive and a negative that are both the same amount. So we would say that that is 0 newtons. That's not on, that's 0 newtons, okay? When you add up the forces that are balanced, they add up to nothing, okay? So I should write that down somewhere. Balanced forces sum to 0. How about that? Balanced forces sum to 0. That's important. That's very important. Balanced forces sum to 0. I should probably move this up some. Might be too late. Oh gosh. It's never too late. And then I'm in the way. I'll make me smaller. You don't need to see me very big anyway. Okay, so where was I? Back to this. That's for the vertical. Can we sum all of the forces in the horizontal? Well, yeah. In fact, let me move this down. Oh, the y didn't go with it. Why is it? Oh no. Well, whatever. It's fine. Okay. And then now we need to sum all of the forces, a summation of all of the forces in the x, horizontal. Well, we have force of friction, plus we have force of air. Now the question is, what do those add up to? What do those add up to? Well, look at the diagram. Are they balanced? Are those two forces balanced in the horizontal? No, which is why we had a ball that was speeding up, right? We had a ball that was getting faster, changing velocity, changing its motion, which means the forces are unbalanced. Well, what does Newton's law tell us about unbalanced forces? Well, the unbalanced force is equal to m times a, mass times acceleration. That's what goes here. Oh no. Oh no. I gotta erase that. Oh, jeez. Oh, so that is m times a, mass times acceleration. So what does this mean for us? Well, that means, oh no, this thing's in the way down here. I gotta get this extended. Extend the page. It won't extend. Oh, there. So that means, I gotta write this now. So now we're saying, hey, unbalanced forces sum to ma, mass times acceleration. They sum to ma, okay? Balanced forces sum to 0. Unbalanced forces sum to m times a, mass times acceleration, the product of ma, okay? This right here, when you add those up, when you add up everything that's acting, now I want you to look at this because this is critical. Is all of the force of air that's acting on the ping pong ball making it accelerate? The answer is no. Some of that force of air on the ping pong ball is being counteracted by a friction force that's opposing the force of air. So when you take everything that's happening in the positive direction plus everything that's happening in the negative direction, the end result, the net result, the net force, or the unbalanced force, that's equal to the ping pong ball's mass times its acceleration. Mathematically, algebraically, that's what it means. Okay, that's what this whole balanced and unbalanced thing means. Now, I know this part looks very complicated, looks very scary, maybe to some of you. It's really not. It's not that big a deal. You'll, as we go through this, it will make sense. Now, in terms of like the actual ping pong ball lab, you all knew that back in like the 5th and 6th grade. Okay, you knew that how much force you push something with is going to affect how it moves. You also knew that how massive the object was going to affect how it moves. So that shouldn't be any major surprise. Newton's second law is something maybe that you knew a little bit conceptually, but now we have the ability to put some numbers to it. Okay, so that is what we talked about today, and then I posted an assignment which is on Classroom. I think that's yes, that's what we talked about. Now, here's the other thing. I did do one more little example when I was talking about net. This idea of net force, I don't mean like a net that you fish with and you need a net because you're going fishing. I mean, net means the end result. So net force, we're talking about the end result of all of the forces acting. That would be the net force. Just like if you have a job and you have a paycheck, let's say you make $10 an hour, let's say $10 per hour, and you worked 10 hours. Then that means you made $100. Yeah? You made $100. Is your check, are you going to get a check that you can cash that is worth $100? Well, any of you that have like a legitimate job and not just paid, under the table with cash or whatever, you'll know that that's not going to be true. You will not actually have $100 on your paycheck. It'll say $100 somewhere, but you won't be able to cash your check for $100. It might be, 80, 89, maybe 89. Darn it, I need to get this video done. It's taking too long. Maybe 89. Oh my gosh, what is happening right now? Maybe $89 is what you get. That would be your net pay. This one's called your gross pay. Your gross pay is what you actually earned. That's everything. The net pay is what you get after all the minuses are deducted. So if you think in terms of this force diagram, the force of air on the ping pong ball is what it's being pushed with. But not all of that is making the ping pong ball accelerate. We have to take away the minuses here. Okay, there's a certain amount of negative force now that's acting on the ping pong ball that's keeping some of the force of air from being able to make the ping pong ball accelerate. And so it's only the net result, or the sum of all your pluses and all your minuses, that total is how much force is really causing the acceleration. I hope that makes sense. That's what we're talking about with summation of forces. Okay, but when they're balanced, they sum to 0. When they're unbalanced, they sum to MA, mass times acceleration. So that's it for today. There is an assignment on Classroom, worksheet 2, unit 4, forces, unit 4, worksheet 2. So that's that, and we'll see you next time.